So here are the last couple of examples. I always like to sort of, in a way, kind of circle the wagons and remind you about everything that you're able to do right now. And we'll bounce around. These are very similar integrals, yet very different styles. So when you take a look at 13, this is a blast from the past. When you see something like this, 1 over x squared plus 1, this is actually the exact, well, let me rewrite it. Maybe it would be better if you saw it like this, because, you know, order doesn't matter with addition. Maybe it'll jog your memory more this way. That is the exact derivative of arctan. So I'm just remembering that from Unit 1 when we talked about this. It really is arctan. So that is still your responsibility. That is still fair game in Unit 3 for me to present something like this. I don't know where it went. I guess I'll have to write it again. I don't know what happened there. But anyway, this is still your responsibility. Unit 3 is all about integrating and all of your methods. So this is still fair game. So is 14, and if I put an x up there in the numerator, now it's no longer arctan, right? This is the exact, you know, version of what the derivative of arctan is. You put an x up there, and that ruins everything. So what I'm going to do is take another approach and say, you know what I could do is I could let the whole denominator represent u. I'm going for that like log rule, that the integral of 1 over u is natural log absolute value of u. Let me see if it works out. I'm going to do the derivative of both sides like I always do in any u substitution problem, and then I'm going to see how it shakes down, right? My original integral had an x in the numerator that I completely ignored because I let the entire denominator be u. And in its place, in this place of dx, I'm going to represent that by just swinging this around. That's du over 2x. Du over 2x. And this is perfect because it's exactly what I wanted. I needed to get rid of this x variable, and I succeeded in that. I do have an extra coefficient of 2 down there in the denominator, but that's not a problem because I can take that 2 in that denominator out as a 1/2, and then I can integrate 1 over u du, which of course is natural log absolute value of u plus c, and that would be 1/2 natural log x squared plus 1 plus c. Notice how I relax the absolute value because x squared plus 1 as an expression is always positive. So again, this is fair game. Unit 3 is about methods of integration. U substitution is on the table. Inverse trig is on the table. And here we are with 15. This is on the table. Oh dear, like when you put these two things together, now what? Well, we already mentioned that 1 over 1 plus x squared is the derivative of arctan. So I'm actually going to use that. I'm going to capitalize on that. I am going to let that be u. I'm going to come at this as a basic u substitution problem. I always want you to try a basic u sub before you start doing fancier things. There is my derivative of arctan, and I'm going to replace, I'm going to rewrite this to say dx equals, which would basically mean I'm moving that 1 plus x squared quantity over there to the left. So now I have my swap out for dx, right? So I had this integral, and so my original problem was the integral of something over x squared plus 1. I totally ignored that denominator, but I did say, look, that whole numerator I replaced with u. And now I've got a swap out for the dx. The swap out for dx is 1 plus x squared du, which is perfect because these two guys completely cancel out. That is legal. They're kind of both in parentheses here, right? They swap out. And so I am left with just this power rule, the integral of u du. So make sure you actually find the antiderivative here. You've done all of this work. Your antiderivative is 1/2 u squared plus c. And so that would be 1/2 arc tan x squared plus c. There's my antiderivative. So again, you know, this is all your job. This is a basic u sub, but pretty advanced. You know, we're talking about fancier styles of integrals. Our last integral that we're going to work on here is 16. What do you do when all you have is arctan? Kind of reminds you about, like, what do you do when all you have is natural log, right? Like, we know the derivative of natural log. I don't know the integral. That wasn't a common rule I learned in Calc 1. Same thing here. I know the derivative of arctan. I don't know the integral. And that's exactly what I'm asking you for. So I am going to handle this with an integration by parts. Sometimes this is my abbreviation for I'm going to try an integration by parts, and I'm going to go with the thing that I know. I know that I can let u equal the arctan because that is a known antiderivative for me. It's 1 over 1 plus x squared dx. That means the other part of the integrand, which sounds pretty weird, but I'm going to do it, the other part is the dv. Well, that means, yes, you can say that dv is dx. This is legal and appropriate. That would mean when you integrate this thing to find v, that means v is x. This is okay, this is acceptable, everything's great. I'm going to come in here and write what the answer is using integration by parts. Of course, it's u times v. I'm just going to put the x in front, minus the integral of v du. Let's write this a different way. So here I have part of my antiderivative, x times arctan of x. And here's the other part that is like to be determined, right? Can I handle this integral? And the answer is, of course you can. This is a basic u sub, right? This is back to basically what question 14 was, right? This is a basic u sub where u equals the entire denominator. This is lovely when you switch it around because all you have is that extra 1/2 flying around, that this is going to be 1/2 natural log absolute value of u, and then your constant of integration. What I don't want to forget about is that this other term is also part of your antiderivative. Okay. So that's a lot of work, So sometimes, you're going to use u substitution in an integration by parts problem. Sometimes it's just going to be u substitution. Sometimes it's just going to be a basic integral. You have to be very fluid and flexible with one little change to an integrand changes your method and changes your structure. Okay, so that's why I like this page. A little bit of difference, but a good variety of skills. Okay, here's our last integral. This to me is the highest level of an integration by parts question. This is certainly something you cannot think of as a basic integral. That is an exponential with a trig function. That is fancy, that is advanced. It does not work with a basic u sub. You're going to have no hope. If you let u equal the sign, you're not going to get rid of the exponential and vice versa. I can think integration by parts. This is not a good structure for a tabular method because you need a polynomial piece to use tabular method, and this is lacking that. So I am going to get started. I'm going to do something, and I'm going to do my best. I'm going to take part of the integral and make it u, and the other part and make it dv. So I have a tendency to look for the hardest part that is manageable to integrate, and I notice it here. I'm going to let that be dv. I'm going to let dv be e to the 2x dx. We've done that a couple of times recently, right? I can integrate that to get v, and it's a little u substitution. I'm gonna do it in my head. We just did it in a couple of recent problems. It's 1/2 e to the 2x. That means the other part that I didn't use must be the u. So again, everybody has a different style. I try to find the most intricate part that I can integrate rather easily. And then the leftover part is the u. And this is a pretty easy derivative. Derivative of sine is cosine. So this is great. So I'm going to get set up, and I'm going to get started, and we're dealing with this really advanced integral here, which is going to be, I can't say it enough, u times v minus the integral of v du. This is how you memorize something. You just keep writing it over and over and over again. So let me write what I'm doing. Integral of e to the 2x times sine x dx. What does it equal? U times v, so 1/2 e to the 2x times sine x minus the integral of v du. So v is 1/2 e to the 2x cosine x. Okay, here's where I'm at. I have part of my antiderivative right here, and I have the other part waiting to happen, right? I'm going to play around with this, and let's compare it to the original. It's not any worse than the original presentation, right? It's kind of equally awful. So I don't know if I'm going in the right direction or the wrong direction, but I'm going to keep going nonetheless. Let me plug in my laptop here so I can finish this video. All right, there we go. So I'm going to actually have to use that approach of like, oh boy, I might actually have to do integration by parts more than once. So let me wrap some parentheses around here, and let me go with a consistent set of criteria, right? I'm going to let u equal the trig function, and I'm going to do the same thing I did in the last problem. I'm going to let dv equal the exponential. Now again, we know the integral of e to the 2x is 1/2 e to the 2x. There's already a 1/2 here, so when I integrate this, right, to get v, I'm going to have 1/4 e to the 2x. And of course, the derivative of cosine is negative sine. Okay. So let's play around with this. Remember, I have part of my antiderivative here. I'm just going to carry on through. So let's start with that. I'll go back to blue. And now I'm going to do the integration by parts in here, right? Okay. So in here is where I'm going to have the u times v, so I'll work on that. 1/4 e to the 2x times cosine. 1/4 minus the integral of v du. And that's too many negatives here, so I'm going to clean this up, right? Okay, here's part of my antiderivative. Now, I have this negative sign here. I don't know how to, I have this negative on this term and this negative on this integral. So I want to be clear about why I'm doing what I'm doing with the signs here. Negative 1/4 e to the 2x cosine of x plus the integral. Well, let's see. Minus is plus, but now I have this extra minus in here, so I'm going to go back to a minus. That's a lot of signs. Okay, and I'm going to write 1/4 e to the 2x sine x dx. Okay, now all of this is trying to get the integral of e to the 2x sine x dx. This is interesting. I want you to notice what just happened to us. Look what I see taking shape of this thing that I still have yet to answer, right? I don't know this. Well, this is pretty wild because that was the original question that you were given. Now, that doesn't mean I did anything wrong. It actually doesn't necessarily mean you're moving in the wrong direction. I need you to see this as a very fancy algebra question. Here's how I want you to see this algebra question, and then I'm going to erase it when I'm done writing this as an algebra problem. I want you to see that you really have some unknown thing, I'm going to call this A, equals something, I'm just going to put a question mark, minus something else, and then minus 1/4 of that thing. You can solve this just by getting your variables on one side. Let's add 1/4 A. So a plus a quarter a is 5/4 a, and then all I have to do to solve for a is just multiply by 4/5. I don't mean to be very abstract here, but I want to be really clear about what's happening. This is not a terrifying situation. I want you to see it as this is my unknown, and I ended up getting the exact same unknown, almost, just a coefficient issue, over here in my answer. So I'm going to cut what I just did there. You might need to replay the video to say, what was she talking about? I'm actually, bizarrely, going to come in here and say, I can handle this. Let me just move this integral. If I have minus 1/4 e to the 2x sine x dx, let me just cancel it on this side. Whatever you do to one side of the equal sign, right, this is a true statement, you have to do on the other. And you know what? Let's take that 1/4 and put it on the outside of the integral. It's the same thing. I'm going to add these together. What do I get? I get 5/4 of this integral of e to the 2x times sine x dx. Now, part of my answer are these guys in blue. I'm going to change the color. I'm not doing anything here. These are part of your antiderivative. We just happen to use integration by parts. But these have been annihilated. That was the whole point. You kind of move that integral over to the other side. So your game plan or your goal in this problem was to try to find an antiderivative for e to the integral of e to the 2x times the sine of x. That's this. You want this by itself. So you're just going to get rid of this coefficient. You're going to multiply both sides by the reciprocal because this cancels out to 1, right? But whatever you do to one part of the equation, you'd better do to every part. As long as you multiply everybody by the same thing, you have not changed the equality statement here. So you are at the finish line. Your goal here was to get the antiderivative for e to the 2x sine x dx. You have accomplished that goal. I just need to clean it up. 4 over 10 is the same thing as 2/5 e to the 2x sine x, and 4 over 20 is the same thing as 1/5. And then I'm going to slap the plus c on it, and you are done. This is definitely by far the fanciest integral of integration by parts. It's what I like to call like an identity integration by parts, meaning you see your questions show up in your answer. Certainly fancy, certainly time consuming, and as we move through chapter 8, a lot of these integrals do become rather time consuming. But you don't want to ever forget your basic structure on how basic integrals work. We're not abandoning that. We're doing that in addition to learning some of the advanced techniques.